Hello everyone, I'm Rhee, the host of today's web seminar. So today we have two professors to give the talks. And the first talk is given by Professor Rhee, and the title is Televerse Teleport to the Augmented Real-World driven by 3I innovation. And so let me briefly introduce Professor Rhee. Professor Taehyun James TJ Rhee is the Director of Computational Media Innovation Center, Associate Professor, Tenure Full Professor in U.S. System at Faculty of Engineering, co-founder of Computer Graphics degrees at the School of Engineering and Computer Science in Victoria University of Wellington, New Zealand, and the founder of the mixed reality startup DreamFlux. He worked in the immersive and interactive technology sector over 25 years across academia and industry. He worked at Samsung as their principal researcher and general manager to lead their computer graphics, medical physics research at Samsung Advanced Institute of Technology, and a senior researcher and senior manager of Research Innovation Center at Samsung Electronics. He served as the general chair for Pacific Graphics 2020 to 2021, XR chair for SIGGRAPH Asia 2018, and executive committee for Asiagraphics Association. And so let's welcome Professor Rhee to give the first talk.
Thank you for the nice introduction, Rhee. I will start to share my screen. Hope it's okay. Can you see my screen?
Yeah.
Okay, great. So Kiora, hello. My name is Taehyun James. People call me TJ. Thank you for inviting me for I think this is the last Asiagraphics webinar for this year. I live in Wellington, New Zealand, and now I'm currently in Seoul, Korea for my vacation. This would be my last talk of this year, and hope this talk would be ideal to wrapping up this year's talk. Today, I will introduce a new term, Televerse. This is our research framework as the future of Metaverse for virtual teleportation and augmented telepresence. This term has been announced and introduced at SIGGRAPH Asia 2022 in Daegu a few days ago. And the core research in Televerse has three keywords: immersive, interactive, and intelligent. So I will skip this part because Rhee shared a great introduction for me. And as introduced from Professor Rhee, now I'm working as a Director of Computational Media Innovation Center. Shortly, we call it CIMIC. So our vision is to be a global hub for digital media frontier, and we work for future targeted research, stay beyond the cutting edge at the immersive, interactive, and intelligent technology, or start with I, so we call it 3I and 3I axis. And we also develop a pipeline to transfer research impact to the industry value. So our current research is in three research teams: augmented telepresence, we name it a Televerse, and digital twin and AI effect. I will introduce our research in augmented telepresence and a little bit about the AI effects today. I will start with a short concept video to showcase the Televerse concept. Yeah, this is concept video, and the actor are our student and researcher, not a professional actor. I hope you enjoyed it. Okay, what is Televerse? Televerse is not a virtual world. This is a real world where we live, and Televerse is a actually digital copy and twin clone of our real environment, so people can virtually teleport to and from anywhere in the world. Their telepresence is augmented by digital information in Televerse, as like a visual effect movie. Why the Televerses matter? The current Metaverse is to meet in the virtual world as avatar, but Televerse, we can meet in the real world created by real-time 3D capturing, modeling, and streaming. And in the media technology point of view, I feel the current Metaverse has been advanced from the animated film, such as Toy Story, because this is fully virtual storytelling with CG creature in CG world. And movie is for recorded media, so no interaction with linear storytelling, but Metaverse is different because it's an interactive online media platform. So we can build a story in live with connected people. But how about Televerse? I feel Televerse can be a real-time live framework advanced from the movie visual effect pipeline. In movie visual effect film, we capture real-world live action, then blend virtual object for creative storytelling. So our high-level strategy to realize the Televerse is to transform the offline movie visual effect pipeline into real-time live platform and connect it with social network platform like Metaverse. So I'll talk a little bit about the visual effect pipeline. This is a part of the behind the movie scene of Hobbit from the FX guide. In this scene, we have an actor and a 3D troll. The actor is in the studio set, and the troll is in the digital world as the 3D virtual creature. But after having proper lighting, rendering, and blending, virtual and real are co-presented in the Middle Earth. If we have fully immersed in the movie, we also feel telepresence in the story. So for making the nice visual effect and then high fidelity mixed reality scene, there are several technical challenges. And film we use rendering techniques such as ray tracing and path tracing. And this algorithm is based on the light transport simulation. And when we have an intersection point of each ray with the scene, we evaluate the rendering equation to compute the color of the intersection point. In particular, for seamless blending, we need to use the real-world light. We use computer vision method to extract light information and render the scene with image-based lighting. And then finally, we blend the rendering into the real-world background. But augmented telepresence require real-time visual effect. So we need to have two keywords, immersive and interactive. This is an example of telepresence with 360-degree video. It enables a wide field of regard and telepresence at the captured spot, but the interaction is quite limited. This is augmented version of 360 video for augmented telepresence. As you can see, we have real-time blending of 3D asset. Using the consistent lighting, shadowing, and realistic rendering and composition, people can have illusion to play with scene object in their telepresence. So our high-level strategy, as I mentioned that before, is to realize Televerse is to transform the movie visual effect pipeline into attractive media platform. So actually, the place that I'm living is quite ideal for doing this. So Wellingtonians contributed 50% top 10 highest grossing film in the global movie sector. I think it might be 60% soon. Contributed because the current Avatar is quite popular. So Avatar 2 and Avatar 3 and Avatar 4 is coming. The percentage can be larger. This is based on the Oscar-winning visual effects company in New Zealand, which is Weta Digital, Weta FX, and Weta Workshop. Especially New Zealand movie industry is specialized for visual effect, which can augment a live action film captured from the real world footage with seamless blending and computer generated imagery. So live visual effect has extra challenges because we need to have whole real-time pipeline for entire visual effects pipeline. And also we need to have automatic solution to remove any manual tuning. And we wanted to have immersive solution for high fidelity final output. And there are many challenges, and this is a good topic for research. So the first thing that we use for the real-time performance is to optimize the resource and computation for human visual system. We try to find the perceptual treasure to optimize resources and computation for human visual system. For example, after a series of the perceptual user studies, we observed that human eyes are not sensitive to perceived composition abnormality, although we reduce the size of light map. So we could reduce resolution of the light map almost 90% compared with a typical visual effects studio setup. But people could not find the abnormality in our user study. So based on this finding, we optimized the image-based lighting. And based on result, we produced almost over 500 frame images per second with various roughness level and lighting condition. And we can use it for a real-time version of the image-based lighting. So we integrated our image-based lighting into the Unreal Engine and Unity as the plugin. And then we added a module to detect dominant light to cast the shadow. And finally, we blend the rendering into the background of real footage. So we adopted Paul Debevec's differential rendering algorithm into 360 video setup. And then finally, we integrated the whole process into a unified framework called MR360. It can be regarded as a compact visual effect pipeline for real-time processing, including lighting, rendering, and composition done automatically. This is an example of MR360. MR360 provides an easy toolkit for content creation. So lighting and shadowing are automatically adjusted. So content creator can easily drag and drop the 3D asset to blend them into 360 video. This is an example of our live demo of Augmented Telepresence made by MR360 Toolkit. People can virtually teleport to Wellington Civic Square and play with fish. So this is a kind of a experience that they cannot have the real world, but they can do in the Televerse. So I covered two keywords so far, immersive and interactive, and I wanted to add one more keyword, intelligent, for providing the more intelligent, smart solution for Televerse. So as I mentioned, the rendering is a process to produce images from the given 3D scene in computer graphics. The inverse rendering is the opposite process. Given an image, we extract scene information such as camera information, light, and texture and geometry from the real world. The inverse rendering is, I think it's a kind of overlapping area between computer graphics and computer vision. And in this talk, I will focus inverse lighting, which is quite specialized for the visual effect. So we construct a real world surrounding light from the limited input is called inverse lighting. For high fidelity augmented reality, we need to estimate 360 surrounding light as a radiance map of the real world from the conventional photograph by took from the mobile phone, for example. So we try to solve this using convolutional neural network. So our method is to train convolutional neural network to learn relationship between the input as the partial view image, like a picture from the mobile phone, and the output as the 360 radiance map, like environment map. Especially our method is to estimate reflection maps, which can cover the material variation in different roughness level, as well as the light information like Radiance Map. So we train neural network for the diffuse reflection map first, and progressively advance the network to estimate mirror-like reflection map. We implemented it using a stack CNN. So train the diffuse reflection map using CNN, then transfer the learned weight to the next CNN. Then we keep doing it until training the CNN to predict mirror-like roughness level. So this progressive scheme provides a good initialization for each reflection and also improve the overall quality. This is a result. Left is the input partial wave image we can take from a mobile phone, and from the top, ground truth, our method, result of our method, and the previous state of art. So as you can see, the estimation result is a little bit blurry compared with the ground truth, but it was quite efficient to produce surrounding light for image-based rendering, image-based lighting. And this is another outdoor example. It also provides a plausible output for the image-based lighting. Especially the indoor is very challenging, but the neural network can learn the relation very efficiently to have a dominant light position and then overall tone quite fit to the rendering. And so even the indoor scene, it shows a very promising result. But however, the light estimation based on machine learning mostly rely on their training set. So it has limitation to adapt input variations such as field of view changes, resolution difference, and exposure and white balance setting. So everything is slightly different in each mobile phone. So we develop a DLNet, dynamic lighting network, to provide a robust light estimation from input variations. So we have a Beijing network with an autoencoder and decoder. Then we add our spherical dynamic filtering framework to generate convolutional filter for input variation. So I will skip the detail for the technical part today. The detail can be covered in our paper. And this is our result in a mobile setup. As you can see, our DLNet estimates surrounding light with a variance of field of view and exposure in this demo. Okay, so we talk about the estimating light. So I will change the topic a little bit for the relighting to relighting. So especially portrait relighting emphasize on adding novel lighting information to the portrait picture. But if the input has extreme lighting conditions such as hard shadow and high highlight, the existing solution causes artifact. So removing undesirable lighting is important for relighting, but this is a more fundamental issue for computer vision beyond the relighting applications such as detection and segmentation and tracking. But the lighting from human portrait image has extra challenge because we might have a glass, we have hair, we have clothes, so there's more variation than face. So we developed a solution for delighting of a human portrait image using deep neural network. Our base architecture for portrait delighting is UNet, and we added a second decoder to learn an offset image. The offset image is the difference between the relight and delight image. It actually contributes to separate the shading and texture in the encoder for more robust delighting outcome. So we use offset image and also add a soft shading image and high frequency mask for our final solution. And this is our final result for our portrait image lighting.
We present some of our D-lighting results, showing consistency under a wide range of illuminations. against the state of the art, if it is more robust to challenging shading features such as shadow borders and reflections. Here we show some examples of delighting in the wild images found on the internet. Notice the removal of shadows and the removal of reflection. We present some.
Okay. So we covered the lighting issue, but at this point, there might be some questions. So our method will start with 360 video background, and also we cover some methods to overcome the 360 limit with mobile phone using image of mobile phone for estimating light. But if the background is 360 video, so the movement during the teleportation is quite limited. We just can rotate our head. So how to move around when teleported is kind of a fundamental issue to solve. So one of the solutions is to jump around capturing spot like a Google Street View in one 360 video to the other 360 video. But the other solution is to freely walk around with panoramic scene. So let's talk about how to work around with panoramic view. So walk around with panoramic view requires 6 degrees of freedom movement, including 4 3D rotation and 3D translation. So we recently presented a volumetric panorama solution for 6-stop navigation. So our method is especially designed for capturing the large space. We use a single handheld 360-degree RGB camera, and then we just can walk around because it's handheld camera to capture a large space. So while the video recording is turned on. And then we capture some spot and estimate the depth using the structure from motion. And then we synthesize novel panoramic view in real time for 6-stop navigation. So I will skip the detail of each step, but I will show the final result for 6-stop navigation and how to capture the scene with our method.
We unlock freedom of movement in video using our volumetric panorama solution. Users can freely move away from the pre-recorded camera position, exploring the environment as if they were there walking around. 360-degree videos provide users the ability to immerse themselves in environments. Users can freely look around, but cannot walk away from the camera position. While we could move the 360 camera through the environment during the recording phase, users will still be locked to the pre-recorded camera path. Here, we can enable our volumetric solution running in real time, breaking away from the pre-recorded camera path indicated by the spheres. Here's another example of an office. Let's move our camera to an extremely far away position to show the volume of our solution. As you can see, this will allow users the ability to freely explore the environment with both head rotation and movement. Simply capture a video of the surrounding environment using a conventional 360-degree camera. After capturing, we can explore the office with full freedom of movement. This includes walking and looking around in all directions. We support casual and accessible handheld cameras, selfie sticks, and tripods to capture environments beyond the room scale. Users can freely explore large-scale environments. They can even explore large outdoor environments, such as an entire park.
So this demo was captured from our version integrated Unity. So we cover some technology for immersive and intelligent and interactive keyword. And now it's time to discuss how to merge these 3 keywords, immersive and interactive intelligent solution into the interactive system. Especially to enable remote communication and collaboration to connect people in Televerse. This is another concept video for remote workspace using augmented telepresence in the Televerse concept.
Imagine being able to appear next to someone the moment they need help. A business's success is driven by the skills and actions of its employees. But to work effectively, they need to be able to communicate easily and accurately. Some problems require complex hands-on problem solving and are ill-suited for video calls. When employees face a difficult problem, they need to be able to ask for help even if those people aren't nearby. That's why we created AVT. Now you can really be where you are needed. Move around with total independence, view from any angle you want, and use augmented reality tools for maximum effectiveness. Using virtual teleportation, you can contribute to solving problems as if you were really there. Upgrade the way your team collaborates and allow them to work at their full potential.
So in this concept video, we use asymmetric setup. What that means, in the video, the remote people who teleport to the working site wear the VR headset to have immersive telepresence at the remote work site. On the other hand, the local people who are already in the work site wear the AR goggle, see-through display, and they see the avatar of a remote person, and then they have a face-to-face communication. So this is a mixture of augmented AR setup and VR setup in the mixed reality environment. So this is a capture live demo, not a concept video from the local host view. The yellow avatar here is the teleporter from the remote space, and the local host and the teleporter communicate face-to-face and collaborate the mixed reality space. And this is another example of remote training. Remote engineer can guide the student to fix the lab equipment. Collaborator can use various visual cues for better face-to-face communication, such as the digital twin of the lab equipment and pointer and gesture through the avatar. So this is a working version of the demo. And now, so it's time to discuss how we can apply this kind of technology and system to the actual application. But actually, application area of the Televerse and Augmented Telepresence is very wide. So it can be different in each country and in industry sector. But I would like to introduce few application areas that we identified in New Zealand. The first application area is the live event. But in the live event, there are a few subclasses. One is to broadcast live event to remote audience. The other is to allow remote performer to be in the live stage. And the final is to provide a mutual communication between people at the event and the one in the remote. In Asiagraphics and Asiagraphics Asia, our team presented several live demo in the real-time live and via AR event. I will shortly share a part of a video for our virtual booth presentation in the real-time live Asiagraphics 2018.
Awesome. So you can see that it's as though I'm in the virtual booth with Steven and Lohit. So looking at the booth right now, it's a little bit empty, so what I'm going to do is add a few objects to kind of add to my video. So we're going to have a table, we're going to have a chair, we're going to have a little real-time live object, and some plastic materials. Oh yes, and also we need a banner, and special thanks to our sponsors, Samsung and NVIDIA, for helping us out. So you can see that it doesn't look too bad. With our lighting solution, we're able to naturally blend digital objects into the video. And so as a designer, it's really easy for me to more accurately pre-visualize what I'm trying to do, as well as keeping immersed in my task. So obviously this is a virtual booth, so we don't have to stick to regular objects. What we can also do is add something more interesting. So we've traveled all the way here from New Zealand, so it would be a shame if we didn't bring some New Zealand flair over here. So I'm gonna add a couple of, ferns to the scene. Awesome. Got a log. Ooh. Yeah. And of course we need a booth mascot, so here's a kiwi bird. Awesome. Okay, so basic layout is done. I'm quite happy.
And recently we tested our asymmetric framework for the live concert in Auckland, New Zealand. We developed a system called the Telefest. Telefest allow multiple 360 live input and control and provides an easy tool to blend virtual asset for real-time visual effect. Then the system can stream the augmented 360 video channel to internet. So we applied our Telefest into the K Festival in 2020, a hybrid concert at the auditorium in Auckland, New Zealand. And K Festival hosted a couple of thousands of in-person audience, as well as a 2,000 online audience. We set up 3 live streaming 360-degree cameras at the stage left, right, and the middle of the crowd. And at the concert, we added a live visual effect and streamed 4 360 video signal to YouTube 360 channel. This is example of the remote audience view. As shown in the right, we added a tiger on the stage next to the performer. Even we filled the auditorium with the water and float the turtle ship. And this is a video of on-site producer view that I captured. So the other important application in New Zealand is tourism. This is our early stage case study in 2017 for virtual tour. People sit in the tri-show in the image with VR headset and control at the Wellington Airport. Then they can virtually visit to the destination of Singapore Airlines and experience the local culture with augmented telepresence at the visiting site. So the original installation at the Wellington Airport was supposed to be a few weeks, but was extended for 3 months by the request. And we opened the demo to the public for 3 months, 8 hours per day. And for 3 months, we had no technical fault at all. And today I will show you the very last demo of our team for this year. It was SIGGRAPH Asia Daegu happened a few weeks ago. And this was a real-time live video capture from our team. So if you missed the chance to see the real-time live demo, so this is a time that you can enjoy the real-time live of SIGGRAPH Asia this year. I will turn the video and hope you to enjoy it.
On stage we have a 360 camera live streaming, that's you right now. Yeah, there you go. Hello. Yeah, there's you. And on stage we have Warren Butcher. We've augmented a meteorite orbiting around him, and as you can see, it not only goes in front of him, but it also goes behind him. We've got this mutual occlusion happening. Go around one more time. And if I drop that in front of him, he can also push it along using natural hand gestures. So there's a sense of occlusion and collision detection between the real and virtual worlds. So how do we do this? Firstly, on stage, we have a live streaming 360 camera mounted with a LiDAR sensor providing a point cloud. This is live streamed over the network and into a game engine. Here is the point cloud information projected onto a 360 panorama. You can probably spot Warren somewhere in there. There's one right there waving. All right, so we can't use this directly. There's plenty of holes through it. And for mixed reality, we need to fill that in. So the first thing we do is a few steps where we densify the depth map, fill in the missing holes, It's a little bit noisy, so we added a few post-processing steps to smooth out the edges, add a ceiling and floor to the depth map, and now this is ready to use for compositing. We can put virtual objects behind and in front of real objects. For collision detection, we need a geometric representation with a mesh. This is the auditorium right now. We achieve this by first putting a spherical primitive in the center of the scene and distorting each vertex based on that depth map. This is the result you see now. All right, so that's how we do it. Let's show an example of using this. I want to switch over to a different perspective. The idea is telepresence, so I want to set up a producer and performer scenario where I, the producer, am going to be remotely located, and Warren is going to be locally located with the 360 camera. You, the audience, could imagine you're like a participant that could be online, anywhere in the world, viewing this in real time. All right, so let's get rid of the rocks. We could augment this scene with a bit more interesting content. How about some snow? It is winter time, after all. We could add some snow coverage. As you can see, you're in the snow. It's going up and down the aisles, in between the chairs. We've got a nice geometric representation of the real world, and it's quite fun. I hope you're not too cold out there. Warren's getting a bit cold, so he's put on his hoodie. All right, now we can do collision detection as well, so let's give him something to interact with. Why don't you give those a little push, Warren? So let's decorate the environment a little. It's looking a little festive. Let's make a little Christmas tree over there. Fireplace, it's looking beautiful now. Although the snowman's hat is a little boring in my opinion. Could you make that a bit more interesting? Okay. Oh, the snowman doesn't seem to like that. You're not going to hit it, are you? Oh, Warren! That's not very nice. Let me rebuild that. Alright, well I'll let you two sort it out. Say goodbye now. Alright, that concludes our first demo.
Yeah, actually, this demo is the right timing to see today. This is just one day before the Christmas Eve. I hope you enjoyed it. So this is what I prepared today. I hope you to enjoy the talk and then enjoy the video that I share for some demo. Today I introduced a new term Televerse and then the Augmented Telepresence, and then have some discussion for the live visual effect pipeline, and especially for inverse lighting for solving the problem for light estimation using deep neural network. And then we discussed a kind of method to merge this like immersive, interactive, intelligent keyword together for asymmetric telecommunication framework. And then finally introduces a few applications and then case study that we have done so far. These are the list of references for my talk today, and hope we can work together, because work together we can make the change. I hope we can build the Televerse together. Thank you. Thank you for inviting me, and thank you for having share your time to watching this talk today. Thank you.
Thank you very much, Professor Rhee. Thank you for your wonderful speech. And so now the audience can ask questions. Actually, I have some questions. So yeah. In the live demo you show at the last, so what kind of device does this technique need?
So we have live capturing at the stage, and in order to do that, we have mixture of the two capturing setup. We have live 360 RGB capturing, and also we have LiDAR sensor, which can have panoramic depth. It can have 10 frames per second for the depth image of the environment, and then we merge it together to give the RGBD images for live feed. With using this RGBD information of the surrounding information, we can have occlusion handling and collision detection, so we can have some novel interactive effect in the live show.
Okay, thank you. And so that this technology will be extended to like mobile device that our day people can use.
Yeah, I think the hardware technology is rapidly improving. So currently we have many camera in our phone. At some point, probably, and as you can see in the some 360 camera is very lightweight and a very small form factor. So I think it's possible to integrate 360 sensor into mobile phone in near future. And many phone also have the depth sensor already. So I think that kind of a thing can be done in near future, probably hopefully within 5 years, 10 years. That's my expectation, but I don't know. Let's see.
Okay.
Hi, Ryan. Yeah, this is Li Gang. So can I ask a couple of questions for James? Okay. Hi, James. Yeah, this is Li Gang. So very nice. Yeah, you have offered a very nice talk. Just before the Christmas Eve, just you mentioned that I believe that your talk is the last one in this year's Asiagraphics webinar. Okay, it's amazing that you showed a real-time live demo at the SIGGRAPH Asia this year, right? Just 2 weeks ago, I think.
Yes, just 2 weeks ago. Yeah.
Okay, so you mentioned that you are still in Korea. Okay,
yeah, I'm still in Korea. Yes.
Okay, yes, that's great. Okay, so I have a couple of questions for you. Yeah, maybe one is more high level. So you mentioned the Televerse and the Metaverse. So are these the same concepts, or do you think there are some difference between the two concepts?
So Metaverse is actually, there are lots of definition, and there's a wide definition and then focus definition. But even the wide definition is possible. The current Metaverse platform is mostly focusing on the virtual world. So we, so like Roblox and then Fortnite. So we can meet in the virtual space. This is good. So we have social networking in the safe virtual space, but this can have some side effect to isolate us with real world environment. So the Televerse is more like a advancement of telephone, television, and the teleconference, and then the Televerse is more like a social platform of future of teleconference. So like a similar concept, but the root might be a little bit different. So the base of Televerse is a real world, not virtual world. So we wanted to be based on the real world where we live, and we wanted to add information like augmented reality. But this is in the Televerse, we are going to the other place. So this is not the place that we are living, we are staying. So this is other place that we have telepresence. So the thing that we do is augmented telepresence. So the basic thing for the Televerse is augmented telepresence. So this is slightly different than Metaverse that we are currently focusing on, because the Metaverse is for virtual space, but Televerse is for real space. I think that's a fundamental difference between Metaverse and Televerse.
Okay,
based on my definition. Yeah.
Okay, yeah, it's good. Okay, so in Televerse, so for the applications in Meteor Reality, you have to estimate the lighting condition and also to estimate the three-dimensional space for the fundamental step, right? Okay, so you mentioned the work that you use CM to estimate the light map. Yeah, for the outside scene, right? So I'm not sure whether this method work for the indoor scenes, because the lighting is not directional lighting, but there may have some many lighting or or some not indirect lighting conditions. So can you give more comments on this work?
Yes, the Radiance Map that is used in the film doesn't have that information, but they have as you mentioned, that direct lighting. But in their cases, at the moment, they are using Radiance Map, and then they regard it as like an infinite distance, like a directional light. But this is a conventional setup for rendering in the film industry. But as you mentioned, that there's a limitation because there's no depth information, location information in 3D. So that need to be improved. But the current setup is based on the directional light. And our methods is also provide for estimation of the indoor scene. But as you mentioned, that there's a limitation. This is we assume that this is far away. But when we have a test in the rendering, this is quite work well compared with abstract light that have only just one directional light and the one abstract light. Compared with that setup, the Radiance Map itself was more providing more reliable lighting information for indoor scene as well.
Okay, so thank you. Yeah, maybe due to time limits, I have one very short question. So you mentioned the inverse rendering as well. So the task of the inverse rendering to estimate all the three-dimensional information from the environment, right? So 2 years ago, there's a very hot topic about NeRF, implicit representation. Okay, I believe you have almost aware of that. So what's your opinion about the NeRF and the transitional mesh representation? So just some quick comments is okay.
Yes, so NeRF is good to reconstruct 3D setup, 3D information. But the thing that we try to is to capture the large environment. Yeah. So in order to do that, we have a 360 setup. It's like an in and out capture. Usually enough is out and in capture. So we have large number of the overlapping information for enough, but 360 setup is limitation for that. So there might be some advancement of enough for adapting the panoramic setup. So this is a thing that we are currently working on. And I believe that combination of the 360 and the NeRF can have a more some of a solution for capturing the large environment, but this is like a still ongoing research from our team.
Okay, so I think I have to stop now. Okay, thank you very much.
Thank you.